my name is Nikita Singh, and today we will look into the topic chemical kinetics. We'll just look into the introductory part and some different orders of the reaction. It is a very important chapter, and every year a question is seen from the chapter. So the contents of today's lecture is number 1. First we will see the introduction. Then we will come to the rate of reaction. And then the rate law. And lastly we will see different order of reactions. These are the contents. First, the introduction. Second is the rate of reaction. Third is the rate law. And fourth is different order of reactions. So let us move to the introductory part. Like in thermodynamics, we have seen that there we calculate that if the reaction we are thinking of is feasible or not, that it will happen or not happen. But we have in thermodynamics we have seen we have just calculated if the reaction is feasible or not. But it is not. But it does not give us the full information about the reaction. If the reaction is visible and take years and years to complete, that is of no use. Therefore, chemical kinetics just complete the information about the reaction. If it is feasible, how much time it will take to reach to completion. Therefore, the study of this chapter is equally important. Now, let me give you an example. In the atmosphere, we can see that hydrogen, oxygen both are present. But why don't you see water droplets falling around? Because the reaction is feasible. It has and gives free energy of negative value. But the time it takes for completion is very much. Therefore, we can't see water droplets falling around. Therefore, the study of chemical kinetics is very important. So this is the introduction of this chapter. That it helps us to predict the time at which the reaction will reach to completion. Now, for calculating the time, we calculate the rate of the reaction. So let us see how it is represented. For simply understanding the rate of reaction, you can just compare it with the speed. How we calculate the speed? By dividing the distance with time. Similarly, the rate of reaction can be calculated by dividing the concentration of the reactant with time. So, let us consider the reaction A forming B. Here A is the reactant and B is our product. So what I said that this to predict the time of completion, we will first calculate the rate of the reaction, which can be compared with the speed. So here we can calculate the rate of reaction ROR. It is represented in ROR for small form. Here we can divide the concentration divided by time. This is the common representation of the rate of the reaction from which we can calculate the rate. Now let us come to the rate law. What is the rate law? Now let us come to the rate law. The rate law helps us to connect the rate of the reaction with the concentration of the reactants. Okay? So we can write one line, this law helps us to connect we will keep in mind. Now for rate law, then we will now learn to write a rate law expression. For calculating rate, we should always know how to write an expression for a given reaction. So let me start fresh. So first we will write, the questions come from here also, that they will give you a reaction and ask you to write the rate expression. So let us consider a reaction like just a simple reaction. Now in rate law, how we will write the reaction? According to rate law, this rate of reaction is directly proportional to concentration of A to the power A and concentration of B to the power B. Okay? But the twist is here is that this A and B are not this A and B. They are different. They are the order of reaction, not the stoichiometry. But there is one more law, that is the law of mass action. Law of mass action, which also give us the same expression like this. But there the A and B are the stoichiometry. But here A and B are not the stoichiometry. So I will write some points for you to remember from this part. Okay. So first we will write the reaction. Then the first point is how to write the rate law. That is the ROR. Is directly proportional to concentration of the reactant to the power A, concentration of another reactant to the power B, where we will write here A, B are not the stoichiometry. But remember, if they ask the now we will look into some important points which we need to remember for the exam. Some important points. That is, let us consider first reaction. Now first, how to write the rate law? It is rate of reaction is equal to what? Concentration of reactant to the power A and concentration of another reactant to the power B. And we have to keep in mind that A and B are not the stoichiometry. Are not the stoichiometry here, but remember, if they ask the law of mass action, not the rate law, then A and B will be the stoichiometry. Okay. Now, and one more thing I want to say that in this chapter, in your course, we will only learn about the elementary reaction. So the A and B I wrote in the rate law is also the stoichiometry in the case of elementary reactions. So we can use, in this course, we can use A and B as the stoichiometry, but A and B actually are not the stoichiometry. For elementary reaction, we can consider that they are the stoichiometry. Now let us move to different order of reactions. For now, first I want to say that there are different order of reaction like zero order, first order, second order. Okay, but before quantifying the amount of time, we need to first have some expression, some mathematical expression to solve and get the time. So for calculating rate of reaction, we use two types of equations. First is the differential form. of equation, and second is the integrated form equation. So this two type of expression we will use for calculating the ROR and getting a magnitude value. So let us move to different order of reaction. First we will look into the zero order reaction. Zero order reaction. Okay. Now first we will calculate the differential rate or the differential equation. For differential equation, what I said firstly in the part that x by t, what is it? It is the rate. So in differential equation, we will just take the differentiation of x. Okay. So and it is directly proportional to concentration of a to the power 0. Sorry, I have to mention the equation a to b, where a is the reaction. Okay. So it is 0 because it is a zero order reaction. So we know that n to the power 0 is a constant. Therefore dx by dt is equal to constant. Then this you have to remember for your exams that in zero order reaction the rate is always constant. So we get a graph on this, that is the rate of reaction with time is constant. So these two are important points to be remembered in zero order reaction. And now we will see the integrated equation for zero order reaction. Integrated equation. Okay. So from the differential equation what we got? As we recall that dx by dt is equal to some constant, let us say k. Okay. So the basic integration we will do here. Nothing much. We will integrate it. By integrating, we will get x is equal to k t. Okay. The limits will be from 0 to x and 0 to. What is x here? X is the concentration of product, not the reactant. It is the concentration of product. And what is K here? K is the rate constant. Okay. And T is the normal time. So this is our integrated rate equation. And from this also we can plot a graph. The graph goes like this. It is x by t. The other, here the concentration was of reactant, it is of product. So we can see it is a linear, there is a straight line equation, y is equal to, it resembles a straight line equation, y is equal to mx plus c. With that, this c equal to 0, that is the intercept of the line is 0. So it will pass through the axis and will look like, and will look like this straight. So it is, so this is the integrated equation. Now there is one more important concept from where the questions are asked. It is the half-life. Okay. Half-life, which is denoted by T. Now let us move. This is also a very important topic. That is the half-life. What is a T half? What is half-life? It is the time at which the reactant concentration is half of the initial concentration. That is A, that is concentration at any time T is equal to A0 by 2. It is the initial concentration. Okay. So we have an equation that we derived. We got the equation. The equation was x is equal to kT. Okay. So what we can place in front, in the place of x, we can place this. We can also consider it as x, it is equal to x also, no problem. So it is like 1 by 2 is equal to t. Here would be like t half, sorry, okay? Because we are calculating t half. So by the energy, you will get T half is equal to A naught divided by T. Again, this is also an equation that you should remember. So this is all about the zero order reaction. Now let us move towards the first order reaction. It is also same concept, but here dx by dt is a to the power 1 because of the first order reaction. Now we will consider the reaction as usual a is equal to b. Okay? So t is equal to 0. Let us consider it is a, the amount present in it, and obviously there is no product. At t is equal to t, let us consider that some x amount is consumed. So here what we will call x amount is 1. Okay? So in the rate equation we can write
I will.
Okay? So in place of a, which is the acceleration, we can write this. Okay? So dx by dt equal to 3 minus x. We will bring it here to integrate a into dt. Now we will do simple integration. There is not much integration involved. Now let us consider it as 0 and a naught, 0 and t. So from here we will get now by just integrating, and it is simple integration, by integrating we will get the equation like x is equal to 103 by t ln log of a naught by t. This is the initial concentration, this is the final concentration, this is the time, and this is the rate part. So it is the integrated form. Integrated rate equation, and this is the differential. So in this lecture we will just learn about this, and I hope that you learned something new from me.